Hi, thank you for tuning into my talk today, which is on designing a catalysis curriculum grounded in systems thinking for instruction at the university level. I'm Manoj Ravi, a research staff member at the University of Birmingham, previously with ETH Zurich in Switzerland. Let me begin by quickly introducing you to the term systems thinking. Conventionally speaking, science subjects have predominantly been thought through a reductionist perspective, where we try to understand a complex phenomena by breaking it down into its smaller components. For instance, if you want to explain how a car works, then you do this by individually talking about the parts of a car, each of which play a role in making the vehicle move. An alternate approach is where you recognize the car as more than a collection of parts. So you don't merely identify the individual components, but you also think of their interconnections, or simply put, you see the car as a whole, described as systems thinking. Now, reductionism and systems thinking aren't necessarily two conflicting viewpoints. It's like looking at the same object through a naked eye, the lens of a microscope and that of a telescope. Everything seen through each kind of lens is actually there, but each way of viewing, of course, makes our understanding more complete. Now, we've thought and learned chemistry mostly through reductionism because that has enriched fundamental understanding across all branches of chemistry. However, there is the concern that an extensive use of reductionism results in the disciplinary siloing of chemistry knowledge. In other words, this results in fragmented knowledge domains that are compartmentalized as analytical, physical chemistry, etc., with very little incentive to think of chemistry as a holistic discipline. Interestingly, other science subjects have long started coupling reductionism with systems thinking. For example, systems thinking is at the heart of this cradle-to-grave life cycle assessment often done in environmental sciences. Similarly, in biology, we have the emergence of what is called systems biology. But chemistry as a discipline has been slow to embrace this approach because it was only at the end of 2019 where a special issue of the Journal of Chemical Education was published highlighting the scope for systems thinking. Now, this special issue mainly focused on extending systems thinking to general chemistry with a focus on green and sustainable chemistry. And that is because systems thinking can elegantly illustrate the interconnections between core chemistry concepts and the larger Earth and societal systems. So inspired by this work, I led an effort to think about the implications that systems thinking would have in delivering catalysis course content. Here's a brief snapshot of the typical topics covered in a catalysis course spanning both homogeneous and heterogeneous catalysis. The current style of catalysis education, concepts are almost always taught through real-world examples, so you can't quite critique the reductionist approach for a lack of context, but systems thinking tends to go much further than just providing context-based education. So what really is the objective of our proposal? Students will be introduced to several catalytic processes and reaction mechanisms during the course. But all of this knowledge must not be relayed as piecemeal presentations of information, but through systems thinking, students must be able to identify the overarching chemistry and catalysis concepts. We also want to provoke learners to place environmental considerations at the forefront of their thinking process. So as this learning objective here states, it's about empowering the learner to design better and more sustainable catalyst systems. Now, graphical tools that identify subsystems and show the interconnections between them is an elegant way to develop systems thinking competencies. For example, here are a few subsystems that you might want to take up for discussion in a course unit on heterogeneous catalysis. The objective is to demonstrate how heterogeneous catalysis concepts, marked here in blue, and catalyst synthesis and characterization concepts, marked here in purple, are related with the catalytic process on the whole and also of the environmental and economic factors. Here's the full version of the system-oriented concept map. As you can see, we identify concepts in each of the subsystems and demonstrate the inter and intra-subsystem dependencies. Let me highlight a couple of features of this concept map through specific examples. Now, students are usually introduced to kinetic models such as the Langmuir-Hinshelwood kinetics and the Ellie-Rideal mechanism through several examples, but this does not inform the learner of the relevance of the models in the larger scheme of things, and that is where a concept map comes in handy, because it shows that these standard kinetic models describing the intrinsic rate of a reaction help in formulating the overall rate expression that feeds into the design of a catalytic reactor. So that includes considerations of the volume of the reactor and the amount of catalyst to be used. And of course, an efficient reactor is key to having an efficient process on the whole, which obviously is going to have both economic and environmental ramifications. The map also helps students realize system-level properties. For example, the map shows that the rate of a catalytic reaction need not always be equal to the intrinsic reaction rate, but it can obviously be altered by both physical and chemical phenomena, including catalyst deactivation. By no stretch is this concept map comprehensive. The missing components and interactions constitute opportunities for learners to expand on the map further. Therefore, the map not only serves as an instruction tool, but also has an interactive element to it, allowing students to update the figure as the course evolves. Next, I turn my focus to framing learning activities in a homogeneous catalysis context. So here's a conventionally drawn catalytic cycle for the hydroformylation reaction and a simple think, pair, share exercise based on that. The first part of the activity asks students to analyze the effect of factors like carbon monoxide partial pressure and olefin concentration on individual reaction steps. In the next part, we ask them to think about the effect of the same parameters but on more system-level properties, so like the overall rate of the reaction. And in the final part of the exercise, we deal with the economical and environmental aspects of the reagents and catalysts involved in the process. So for example, to consider the sustainability of using an element like rhodium. So the activity, as you would see, starts off with a reductionist perspective, so individual reaction steps, but builds towards a more holistic perspective, finishing with the consideration of a global system of systems. In the final part of my talk, I would want to briefly touch upon the aspect of student assessments for evaluating systems thinking competencies in a catalysis course. For this purpose, I use the systems thinking hierarchical model as the basis. As you would realize, it's pretty analogous to the Bloom's taxonomy. So you have the basic skill of analysis of system components forming the base of the pyramid and more advanced skills featuring further up the pyramid. So we sat down to formulate assessment questions for a typical paraffin isomerization process, which is catalyzed by platinum-loaded zeolite mordanite catalyst and zeolite A being used downstream as a molecular sieve for separation of the linear from the branched isomers. So to assess the most basic systems thinking skill, we can ask students to identify the real function or role of the platinum on zeolite mordanite as well as zeolite A in this particular process. So the two units of the overall process of the system. The next set of questions will ask students to evaluate the effect of a specific change in one process unit on the other process unit. So that's the way we deal with interrelationships within the system. Finally, for the very high end of the pyramid, we need to test the student's ability to make generalizations and predictions. So for example, to predict process performance on increasing the silicon to aluminum ratio of zeolite mordanite. And that would require the understanding of the hidden dimensions of this system as well. So to conclude, I hope my presentation today has highlighted the enormous potential and scope that systems thinking has in revamping how catalysis can be thought at the university level. Not only is embracing this perspective paramount to help students achieve better learning outcomes, but also to enable them to take a more holistic understanding of the implications that catalysis has in matters of global importance, including climate change and sustainable development. And today, I took you through how incorporating systems thinking in a catalysis curriculum will look like, basing the analysis on the principle of constructive alignment. So starting with how intended learning objectives would have to be reframed, the graphical tools that can be efficiently used, the kind of learning activities that can be designed to initiate systems thinking competencies, and finally, the considerations that would have to be kept in mind when formulating student assessments. With that, I would like to thank you for tuning into my talk today and hope it was worthy of your time.
Finally, I would like to thank the RSC Higher Education Interest Group for awarding me a bursary to attend this conference, and I really do appreciate their efforts to encourage first-time participants like me to attend this conference. Thank you.